Hi guys, welcome back to Data Every Day. Today we're looking at a data set of news articles. Um, and basically we have some headlines and categories of each article. Just give me 1 second. Lift the shade up. Okay. So there's a bunch of different categories. I think there's 41 in total, and we're going to try to predict the category of a given article based on the headline alone. So it's a bit of a difficult task, I think, because some of these headlines may be somewhat short, but hopefully we'll get some interesting results. So I'm going to hop into the notebook. We are going to use NumPy and Pandas for working with the data. For visualization, we'll do a confusion matrix at the end. I'm going to use pyplot and Seaborn. And then for preprocessing, we'll be using the tokenizer and pad sequences function from Keras and the train test split function from sklearn. Then for building the model, we'll use TensorFlow and evaluate the model with the confusion matrix and classification report from sklearn. So let's go ahead and load in the data. So we're actually dealing with a JSON file today, and I believe it's new line delimited JSON, which means we'll have to use the pandas.readJSON function, pass in the file path, and then type lines equals true at the end. I think it'll give us an error if we don't have that there. So let's load it into data. Oh, actually, I forgot the imports. And then let's take a look at it. So okay, there we go. Just loading it in. So we have 200,000 rows, a category for each article, a headline, and then the rest of the information we're not going to use. So we're just going to deal with these two columns. So let's just check for missing values, get a little more information with data.info. We have no missing values, and we'll just be using the first two columns. So before we move on, I want to make two variables that will be useful to us throughout the notebook. So one will be a label mapping. This is what are we going to map each label to. And the reason I'm doing this is if we look at the category column, which is our label column, you can see we have a lot of different labels. So I want to create a mapping that's going to map each of these labels to a unique integer, because that will, it will help us enumerate the classes, but TensorFlow also requires that they come in as integers instead of strings. So we can do this by using the enumerate function, and then this will actually return an enumerate object, so we want to turn it into a dictionary after that. And now we can see an integer is being mapped to a label. However, I want it the other way. I want a label mapped to an integer. So what we'll do is call this label mapping. And then I'm going to say label mapping. Well, okay, let's call it mapping. And then our label mapping is going to be value to key for a key and value in mapping.items. So it's just flipping key value into value key. So it's going to flip all of the elements of the dictionary. So if we look at this, you can see now we have a unique integer assigned to each label. I'm also just going to get the number of classes, which I'll call num classes. That will be the length of our label mapping. And we can check that. Maybe I'll print it out. Num classes, or number of classes. We should have 41. Yep. Alright, so let's start preprocessing. So I'm going to create a function called Preprocess Inputs that's going to do it for us so that we don't have to modify the original data. It's going to take in a data frame and a label mapping. First thing I want to do is copy the data frame so that we're sure we're not modifying the original. And we want to use only the headline and category columns. So we can do that with df equals df.loc. In order to slice the data frame, I'm going to target all rows and just headline and category. And let's return df here. So we'll store the processed version in X for now, and we're going to call preprocess inputs on data. Okay, label mapping equals none by default. Alright, so this is our data set. We have 200,000 rows, which is quite a good amount of data for our purposes. However, I'd like to take a look at the class distribution. So let's take X subcategory and take the value counts of the classes. Alright, so we have 32,000, 17,000, 16,000, and then all the rest are under 10,000. At the bottom we have just down to just 1,000. So we do have a class imbalance here. It's very, very heavily skewed towards politics and wellness and entertainment. And then it sort of trickles down after that. So to address this, because I don't want to worry about the class imbalance, I'm going to undersample all of the majority classes. In fact, I'm just going to sample 1,000 samples from each class, so that we'll have an even class distribution. So I'll say that here. Sample 1,000 examples from each category. So to do this, what I'll do is create a list, empty list called category samples. That's just an empty list. And then for every category in df subcategory.unique, so essentially for each unique value, we'll create a category slice, which is going to be a slice of the data frame where the only containing categories of that type. We can use the query function for this, where we're going to query the function where category column equals, and the value we want to pass in is this actual category here. So you can reference environment variables with the @ sign like that. So when category column equals our category value, this will be all the rows of the data frame just containing that condition. Then we'll sample this. So we'll sample the category slice. We'll sample 1,000 examples from the category slice and save that data frame into category samples. So I'll just do it this way: category samples dot append. So we're going to add to this list category slice dot sample 1,000, and I'll include a random state so we can reproduce the results. So now for each unique value we should have 1,000 examples of that type. Now when we're done with this, what we'll do is add them all into one data frame with pandas.concat, and we'll concatenate all the category samples along axis 0, so on top of themselves. And we'll call this df, so we'll store that back in df. And then I want to shuffle that, since at this point they're all in order, so I want to mix them up. So I'll sample again, this time with a fraction of 1.0, which means sample all the data without replacement, same as just a shuffle, and include a random state so we can reproduce the results. And the last thing I want to do is reset the index so that we just have consecutive indices. And drop equals true will prevent the old indices from becoming a new column. Alright, so now we have 41,000, and you can see that's 1,000 for each class. If we look at this, we now have 1,000 examples in every class. Okay, so we've dealt with the class imbalance. Now we're going to map the labels to integers. So for this we'll use the label mapping. We're passing it in here, df subcategory equals df subcategory dot replace, and the replace function allows us to specify a mapping as a dictionary. We already have the dictionary, so we're going to pass in label mapping here. So if I run this and I want to now pass in our label mapping, then if we look at our categories, we now have integers, and we have 1,000 of each integer. Alright, so we're almost done. Now we got to deal with the headlines. So from this point on, I'm going to do the train test split. So we're going to split df into x and y. Y is going to be what we're trying to predict, so that's just the category column. And the x is the headline column, that's our inputs. So right now these will be pandas series. Then we will do the train test split with the train test split function from sklearn. We're going to pass in x and y, specify the size of our train set, we'll say 70%, include shuffle equals true, and give it a random state. This will return 4 new sets of the data: x train, x test, y train, and y test. And let's return these values. And we'll take a look at x train. We should have shuffled data, just the headlines, and 70% of the original data. So if we look at x train value counts, we should see about 700 in each. Oh, actually, this should be y train.value counts. Yeah, so there's about 700 in each since we did the train test split with 0.7 train size. Alright, so right now we have every headline as a series of words. We have to think of a way to encode the words so that the model can work with them, because it has to be numeric, right? So one way to do that maybe would be to encode each unique word as a one-hot vector. This is known as a bag of words model. Basically, we take all the unique words in our train set and send each word to a different vector. So a given vector would look like this, where each space represents a different word, and 1 means the presence of that word. So each word has this is called a sparse encoding. The problem with the sparse encoding is that it's very memory inefficient, but it also doesn't preserve relationships between the words. So what we're going to do instead is called a dense encoding, and that's using word embeddings. So word embeddings sends each word to a new vector in a vector space of our choosing. And we don't actually have to worry about where to send them. The model will learn where to send the words so that it maximizes the information captured by their embeddings. So it will find nice ways to embed the words so that we get high performance in our model. So we can choose the dimension of our embedding. So we could say maybe let's embed every word in 64-dimensional space. Then every word will have a 64-dimensional vector to represent it. So I want to create a function called getSequences. And getSequences is going to take in the texts that we'd like to transform into sequences and a tokenizer object. So let's create the tokenizer object down here. Fit a tokenizer, we'll say. And so our tokenizer is going to be tokenizer that we imported earlier from TensorFlow, Keras. And we'll specify a number of words to use. If we don't specify a number of words here, we'll automatically use the maximum number of words present in the train set. So I did this before. There's about 30,000 unique words in here. And if we were to encode each of these in a sparse encoding, you could see that each word would take 30,000 numbers to encode, because each vector would be a one-hot vector of length 30,000. We're going to cap it at 10,000 just to improve the training time, and it can also improve model performance as it doesn't complicate the model as much. So we're going to cap it at 10,000 here, and then we're going to fit the tokenizer. So we'll call fit on texts, and we're going to pass in x train. So we're only fitting to that train set, so we want to pretend we don't have access to the test set. We want to build a model that can work well in unseen data, so it doesn't rely on the test set for making predictions on it. So after we fit the tokenizer, we're going to pass it into our function up here. So when I call getSequences, we pass in xtrain and tokenizer. I'm hoping that it can return the new xtrain, which will be converting this series of headlines into a NumPy array of integers. Okay, so we're going to do this by using tokenizer.texts to sequences. And we just pass in the texts here, and that's it. This will now be sequences. And if we return sequences now, and I take a look at xtrain, you'll see we have a list of lists, and each list is you can see each word has been converted to an integer. Now the number here represents the frequency of the word. So 1 means it's the most common word in the whole data set. So let's try to see why this might be most common. This is 1, 2, 3, 4, 5, example 5. So if we look at data, actually that won't work. If we undo this then, if we don't get the sequences, and we look at example 5, maybe that word is 2. So 2 might be the most common word it finds. Alright, similarly, you'd see that in and are in here, so those probably have some very high numbers as well. I mean low numbers as well. And yeah, that's 5 and 4. Okay, so the only issue here is that these are all of different lengths. And we need to send in a uniform length vector into our model. So we can do this just by padding the sequences with zeros so that they all have the same length. Only thing is, I want to make sure I'm padding both the train and test set using the same length. So what I will do is include a flag up here. Train, by default, I'll make it true. And if train is true, then we'll calculate the maximum sequence length. And we can do this by taking our sequences and mapping a function to it. So the function we're going to map is to every sequence x, we will take the length of x. And we'll map that to sequences. So we'll just convert each sequence into its length, and then turn that into a list. And then we can just take the max of the list with numpy.max. And that will give us the maximum length of a sequence in sequences. Now, if train is not true, we want to pass in the maximum sequence length. We don't want to recalculate it. We want to know it beforehand. So I'll default this to 0, and if train is false, then we will use the sequence length that's passed in. Alright, so now we'll pad the sequences using the pad sequences function that I imported earlier from Keras. And this, we just specify the sequences and then the maximum length, which will be max sequence length. And we'll include padding equals post just to ensure the zeros go onto the end of the sequences instead of the beginning. Alright, so let's run this and see how this goes. If we get back xtrain, we now have a NumPy array where each vector is of uniform length. So if we look at the shape of it, we have 26. Each example has length 26, and you can see that the end has been padded with zeros. So we want to now get the sequences for xtest, right? The same tokenizer, which has only been fit to our train set, but this time train equals false. So up here, train equals true. Down here, train equals false. And when train equals false, we want to specify maximum sequence length. And we can get that from xtrain.shape sub1, which will be the second dimension in x, which will be this. That's the maximum sequence length. So run this, take a look. xtrain.shape and then xtest.shape, they should have the same second dimension. Okay, so we're good to go. Alright, so I guess I'll leave this on here. And then ytrain. Okay. So now we can start modeling. Okay. Our inputs are ready to go into the model. We have sequences, we have labels. Just say get sequence data. And now we can construct the model. So we want to just we want to embed the words, like I said, using the word embedding. And then once they're embedded, we're just going to do a simple classification from the embedding. So inputs, that's going to be a tf.keras.input. The shape here, shape of our input, is going to be the same as max sequence length, which is xtrain.shape sub 1. Then we'll have our embedding. That will be tf.keras.embedding. So this is the embedding layer that will learn the embeddings for each word. We have to specify an input dimension and an output dimension. So the input dimension is the dimension of the sparse encoding for a word. So if this is basically how many words are present in our dataset. And we cap that at 10,000. So we'll just go in here and type 10,000. The output dimension is the one we choose, at the time of training. This is like a hyperparameter. The higher dimension you choose, the more deep of the patterns you can capture between the words. For something like this, since we don't have too many words, I think 64 dimensions works okay. And we'll pass in inputs. So, layers, tf.keras.layers.embedding. So if we look at inputs, and we look at embedding, we come in with a single sequence of length 26, and each word in the sequence gets 64, is represented then as a vector of length 64. So we end up with an output, a two-dimensional output of 26 by 64. So this is the words and the embeddings for each word. Now we want to flatten it out after that because we need it as a single single one-dimensional vector if we're going to do classification. So we'll do a flatten layer with tf.keras.layers.flatten, pass in embedding. And now down here, if we look at this, you see it's just been flattened out to a single vector of length 1664. Now we'll pass the output of this into our dense layers. So I'll create two dense layers. This will just be the classifier part of the neural network, which will be tf.keras.layers.dense. We'll give it 128 neurons, ReLU activation, and then we'll pass in the output from flatten. Alright, so let's grab that, duplicate it, and just pass in the output from dense 1. And then this one's going to be called dense 2. Then we'll have our outputs, which will be tf.keras.layers.dense. And this is going to return however many classes we use. So I stored that as num classes, so I'll just pass that in there. That's how many neurons we have. And the softmax activation will be used to give each of those values a value between 0 and 1 so that they all sum to 1. And so each value, num classes values, will be probability values for each of the classes. We'll pass in the output from dense 2, and we'll construct the model. Model equals tf.keras.model. The inputs and the outputs are passed in. Alright, so I'll just print out that model summary. And I'll also use tf.keras.utils.plotModel to see it as a computational graph. Dense 2 is not defined. What's wrong here? Oh, should be passing in dense 1 there, sorry. Okay. So here you can see it's just passing through. First we have the input, then it gets embedded, then it gets flattened, and it goes through two dense layers, and we have our final output down here. We can see the weights here on the side, and we can see the shape of the vector as it passes through. Alright, so now we can start training. Just delete these. So we'll compile the model with an atom optimizer. We'll use sparse categorical cross entropy loss. And our metrics here, we'll just use accuracy since it's multi-class. Alright, so we'll store the fit history in history and call model.fit. And we're going to train on xtrain, and the labels are given by ytrain. We'll give it a validation split of 20%. We'll give it a batch size of 32. And we'll train for 100 epochs and use the early stopping callback. tf.keras.callbacks.early stopping. And then we will monitor the validation loss and give it a patience value of 3. So when we see that the validation loss stops improving for 3 consecutive epochs, we'll stop the training and restore the weights from the best epoch. Alright, so there we go. And now we can get the results down here while that trains. First I'll just print out the test accuracy. I'll display it to 2 decimal places and as a percentage. And I'll format that. We can get it with model.evaluate on the test set xtest ytest. And then we're just going to take the second value from that, which is the accuracy value. Then I'm also going to set verbose equals 0 so we don't see the loading bar. Alright, so our model already finished. Now, it doesn't seem to be doing so well, 30% accuracy, but we have to remember we have like 41 classes, so we might still have a reasonable model. We'll have to see. Maybe a confusion matrix can help us visualize that. Alright, so we should put a period here. No, after, and then I want to multiply this by 100 so we see it as a percentage. Alright, so 31.44%. So not so good from just that metric, but accuracy can be misleading. So I'll create a set of predictions, called ypred. And for this we'll use model.predict on xtest. Now, if I look at this now, you'll see this actually has 41 probability values for each example. So we want the highest probability value, and then we want the location of the highest probability value. So we can do that. NumPy.max would give us the highest probability if we take the max over axis 1. Then we'll get the highest probability for each classification. But we want the location, the index of the highest probability, so we'll use argmax instead. And then we can get the actual classes associated with each prediction. Alright, then we'll create our confusion matrix. So I imported this from sklearn. We just pass in ytest and ypred, and that's it. And we'll also get a classification report, which I'll call CLR. That's also from sklearn. We pass in ytest, ypred. So if I run this and I print out the CLR, you can see all the classes are given by just their integer values. So I want to give them the original values. That's why we saved the label mapping. We can go in here and say target names is given by label mapping dot keys, and we want to turn it into a list. So the list of the label keys. Well, now you see we can now have the proper labels associated with each integer. Alright, so let's see this. We're going to plot the confusion matrix and then print out the classification report. Alright, so I'll use Seaborn for this. We'll create a new pyplot figure with a figure size 20 by 20 since we have a whole lot of classes. And then we'll use Seaborn's heat map function to plot CM, which is our confusion matrix. I'm going to turn on annotations, set the minimum value to 0, format this with a G so that we see the counts as integers instead of scientific notation. And then we will give it a color map of blues and turn off the color bar. Alright, so then we'll give it some X ticks. So we want the tick marks on the X-axis and Y-axis to be the label names. So the ticks, this is the spacing of the tick marks, will be given by a NumPy A range whose number of elements is num classes. And we're going to shift them all over by 0.5 so that they end up in the middle of each box. And then the labels are going to be given by this list of keys. So I'll paste that in, and then we'll just copy over the exact same thing for the Y ticks. Alright, then we'll give it some axis labels. So the X label is the predicted values, and the Y label is the actual values. And we'll give it a title of confusion matrix. And show the plot. Alright, last thing to do, actually I'll just run this, and then down here I'll print out the classification report. I'll just copy this. So like that. Alright, actually you can see that they're all overlapping, so what I'm going to do is in here, rotation of the tick marks. For the X, I'm going to set it to 90 degrees, and for the Y, I'm going to set it to 0. That should fix that. Okay, so here it is. So, not too bad actually. What I mean is, for the most part, the model is getting the idea. The diagonal is all lit up, and we do have a lot of misclassifications, but there's only a few really bad ones. So let's actually look at what that is. This one here, this means we are predicting the world post as world news. And I guess that makes sense because world post and world news are basically the same thing. Over here, we're predicting taste as food and drink. So that makes a lot of sense as well. For the most part, the model is actually doing a fine job of getting the classifications in the right categories. Now, it's not to say it is making a lot of errors, especially in some of these classes like Latino voices. I think, right? Yeah, it has quite a few misclassifications here, but these are some of the more niche examples. Arts also a lot of misclassifications. It's predicting a lot more as arts than there really are in the dataset. All right, but so that's if we look at the classification report, the F1 score is sort of a measure of how each example did. Precision is saying out of all of our predicted values, how many did we get right, and recall is saying out of all the actual values, how many did we get right for a given class. And F1 score is a combination of the two. Alright, so that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.